I got a challenge to create a digital thermometer using NTC thermistor, and it is not as easy as you might think. For starters, I chose the tiny NTC thermistor. A thermistor is a type of resistor whose resistance strongly depends on temperature. There are two types of thermistors, negative and positive temperature coefficient, known as NTC and PTC. I am going to use NTC. Firstly, checking the datasheet, we find a formula for constant calculation, but checking more closely, we can already find the constant for our thermistor. This thermistor ends with 1S, so its range is from 25 to 85 Celsius. Then, if we find the thermistor with the appropriate temperature, we can find the constant, which is 3435. Knowing this constant, after rearranging the formula, we can find the resistance dependent on the current temperature. Tr is equal to 298 kelvins. The T is current temperature. Rr is a resistance rated to temperature Tr. Now, all we need is to do some maths in Excel. I chose temperature from -40 to 85 Celsius. I calculated it in kelvins. Then, using the formula, I have calculated the resistance dependence on the temperature. Here, I have depicted the resistance dependence on the temperature in this graph. To see better distribution of points, I have put the resistance in a logarithmic scale. There are two voltage divider circuits, which can straighten out the dependence curve. The first one straightens out better, however, the voltage range is much smaller. The second one suits me better because I will use a 10-bit ADC with whom I cannot capture very small voltage fluctuations. So here we have a output voltage on temperature dependence graph. We can disperse this graph into 3 parts for easier formulas. Now, to get a formula from the main graph, we just have to add a trend line, which would be a polynomial. And after taking some of the results, we can see that the most suitable is a 5th degree polynomial. 5th degree polynomial is a big formula. To make it smaller, as I have already said, we can disperse this graph into 3 parts. First one from -40 to 0, second from 0 to 55, and third one from 55 to 85 Celsius. For these 3 separate graphs, it is enough to have 3 different 3rd degree polynomials. So now I have told you a lot of things and showed you a lot of formulas. And now it's time to explain why am I doing this. First, we calculated the resistance to their corresponding temperatures, and as you can see from this graph, in the low temperature section, we can get a clear resistance value. However, moving to a higher temperature section, we can see that the resistance points are in a one big heap. Thus, obtaining the correct resistance becomes much harder. That's why we use a voltage divider to make our graph as much linear as we can possibly get. And in this polynomial, we can find the values much more easily. Now, one of the main problems was that we had a corresponding temperature values to resistance. However, we could not get values that were in between them. That's why we are trying to get a polynomial function. With this function, we can easily get any temperature calculated from the output voltage. After a few basic tests and a addition of a battery over voltage and short circuit protection, plus a step-up booster, the whole schematic looked like this. Then, with the magic of editing, I designed the housing and put everything together in just under 20 seconds. So I checked some parameters and I had to change the formulas a bit. The step-up booster gave out 5.2 volts instead of 5. And 10 kilo ohm resistance actually had 9.8 kilo ohm, so of course the polynomial changed a bit too. After getting the polynomial, I started programming, and it is very simple. First, we have our own polynomial function here. The voltage is equal to the x in the graph polynomial. We get the voltage by reading the A0 pin, multiplying it by 5 and dividing it by 1023, because that's the value of 10-bit ADC. Everything else is just to control the OLED LCD using SPI. Now that it is done, let me show you how would it look if it would be a selling product. Thermo Friend 1.0 is our most advanced thermometer ever. Beautiful, complex, yet simple. Picturesque and pleasing design includes a small thermistor and a beautiful OLED LCD. It is capable of getting the finest temperatures, meaning a precision temperature to your own comfort. Now, some real testing. For this experiment to be more precise, I added some reference thermometers. 2 analog and 1 digital. One of the analog thermometers had a 1-degree error. So thanks for watching. My videos take quite a long time to make, so if you wanna help me make more, please subscribe and like, cause only 1% of people who watch my videos are actually subscribed. It's free and you can always change your mind later.